Hey guys, Mr. Smith here, and in today's video lesson, we're going to be looking at transformations of the logarithmic function. So in our first lesson of this unit, we reviewed the exponential function, and we looked at its inverse, and we saw the general shape of that inverse, but we didn't actually attach a name to it it kind of looked like this. Right, so for some exponential function like so, we had the inverse. That's not what it looks like at all. Through like so. There we go. And if we had an exponential function, y equals b to the power of x, then we had its inverse function, x equals b to the power of y. And in our first lesson, we just kind of left it there. It has an inverse. The inverse is a function. It can be defined by x equals b to the power of y. In our second lesson, we said, okay, it'd be nice to actually have this equation with the y isolated. And we did that by introducing the idea of a logarithm. And we said y, looks like a g, y equals the log base b of x. And so we have a brand new function. And in this lesson, we're just going to be doing just graphing the log function and some transformations. Do the transformations that we've reviewed and applied to power functions and trigonometric functions, do they apply to logarithm functions? They sure do. And so we are going to just quickly review the types of transformations. I'll add a few notes here. We'll talk about what the effect of these has on the points. But yeah, this is just a review, a little summary of things we already know. Adding a value to the end of the function is a vertical translation. And I'll just write this in with my tablet here. If c is greater than 0, then we shift up by c units. And if c is less than 0, that means we shift down c units. None of this should be new, just reviewing what we already know. What this does in mapping notation is it takes an original point on the function, xy, and it maps it to a new point. And if we're vertically translating something, if we're shifting it vertically, the x value is unchanged. It's the y value that changes, and we add c to it or subtract c to it. This should read f of x minus d. So I'll fix that up for your lesson sheet when I post this. This is a horizontal translation. And if d is greater than 0, meaning we're subtracting a positive number, then we shift to the right. D units. And if d is less than 0, so we're subtracting a negative, so it's like d, or it's like x plus 2 or plus 4, we're subtracting a negative, making it positive, we shift to the left by d units. Again, nothing new, just reviewing. What does this do? It takes points x, y. It doesn't affect the y coordinate. It affects the x coordinate. And we add on whatever d is to the x coordinate. And the y value stays unchanged. All right, next up. When we multiply a function by some number out front, it can have a couple of things. It can be a vertical stretch or compression. And if a is negative, it corresponds to a reflection in the x-axis, like a vertical reflection. And just like we did above, just summarizing, if the absolute value of A is greater than zero, greater than one. So ignoring the sign, if it's a number like 2 or 3 or 1.5, if it's bigger than 1, you get a vertical stretch. You stretch by a factor of the absolute value of A. And if the absolute value of A is between 0 and 1, you get a compression by a factor of the absolute value of A. Same thing. What this does to the points, it's a vertical stretch or compression. It doesn't affect the X value at all. It affects the Y value. Multiply the Y value by whatever A is. All right, so in the same way, multiplying the X by a parameter K corresponds to a horizontal stretch or compression. Again, this is nothing new for you guys, just summarizing all the things we know before we end this reviewing, before we start graphing some log functions. Horizontal stretch or compression, just going to parallel what I wrote above. If K is negative, then we also get a reflection in the y-axis, a horizontal reflection. And the difference here is that if the size of K, if the absolute value of K is greater than 1, we actually get a compression. By, you're going to squeeze this in, a factor of 1 over the absolute value of K. And if K is between 0 and 1, the absolute value of K, then what we get is we get a stretch, a horizontal stretch by a factor of 1 over the absolute value of K. What this does is it transforms the points. X, Y doesn't affect the Y value, does affect the X value. You multiply the X value by 1 over K. Keep the Y value the same. Now, when you put all these together and you graph a function that could have 1 or 2 or 3 or all 4 of these parameters not being 1, we can, so this is just all the transformations. All the transformations. And generally speaking, a generalized formula for points are mapped to, points x, y are mapped to. So when you apply the horizontal stretches or compressions or reflections, the x value goes to 1 over k times x. And then if there's a translation, you would also add on d to that. And for the y values, you apply the vertical stretch or reflections, and then you translate it, add on c. So that's a general formula for how points are mapped. And what we're going to do in this lesson is just get more comfortable working with the logarithmic function, properties of its graphs, and yeah, it should be good. So what I've given for you guys here is I've, on each of these grids, I've graphed the basic logarithmic function, y equals log base 2 of x. So you can see it goes through some key points, 1, 0, 2, 1, and 4, 2, which makes a lot of sense for this function. I have some room here, so I'm just going to write this down. So the dashed line here represents the base function log base 2 of x, and we know that when x is equal to 1, so 2 to what power gives you 1? 0, the point 1, 0. When x is equal to 2, 2 to what power gives you 2? Answer is 1, so we get the point 2, 1. And the other key point, the other anchor point on there you can see is when x equals 4. 2 to what power gives you 4? 2. The log base 2 of 4 is equal to 2. And that gives you those 3 anchor points we see there. What I've asked you guys to do is just to predict what the new graph will look like. It doesn't have to be perfect. So we can see this graph has a x-intercept at 1, 0 and a vertical asymptote at x equals 0. What's the new graph going to look like? And yeah, so I've asked you guys to make a prediction for 5 of these, and then I'll come along afterwards and do the actual graph. So if you want to pause the video and take some time, make some predictions, you can unpause when you're ready, and we'll have a look at what these look like. All right, so I'll assume you given it a try, and let's give these guys a plot. So 2 log 2x. So we know this is a vertical stretch. And so all those points on my basic log function are going to get stretched by a factor of 2. So I'm going to take my anchor points. So 1, 0 is going to stay where it is, right? Because the y value is 0. 2, 1 is going to move to 2, 2, stretched by a factor of 2. 4, 2 will get stretched to 4, 4. And that's the 3 anchor points. Gives us enough of an idea. So it's basically has the same general shape. It's just stretched vertically. Log base 2 of x minus 1. So we know this is a horizontal translation. And we know it's right 1 unit. So we're going to pick up our points and move them right 1 unit. So 1, 0 goes to 2, 0. 2, 1 goes to 3, 1. And 4, 2 goes to 5, 2. Moreover, another property of the graph shifts along with it. The vertical asymptote is going to shift to x equals 1. And so please add that detail to your graph. And so we get something like this. All right. Log base 2 negative 1/2 x. We have 2 things going on. So 1, we have a horizontal stretch by 1 over negative 1/2, which is equal to negative 2. Excuse me, we should the absolute value. So we're stretching things by a factor of 2. Let me rewrite that a bit more nicely. Horizontal stretch by 1 over the absolute value of negative 1 over 2, which is equal to positive 2. So we're stretching this horizontally. And 2, it is going to be reflected in the y-axis. So you could do this in a couple of steps if you like. I might do that for ours. So 1, 0 will go to we'll apply the reflection first. So 1, 0 goes to negative 1, 0, 2, 1, negative 2, 1, and 4, 2 to negative 4, 2. And if you like to do this, you can kind of add that first stage. You can kind of sketch out what that would look like. So this is y equal, actually, I don't want to make it too cluttered for now. So this is the reflection. And then for the stretch, that looks like a nice pink color. We're going to stretch these guys by a factor of 2. So negative 1, 0, we're going to stretch it horizontally to negative 2, 0. Negative 2, 1 goes to negative 4, 1. And negative 4, 2 is going to go to negative 8, 2, which is a bit off the graph, be somewhere like that. And so we'd have a graph that looks like this. Still have the same vertical asymptote, something more or less like that. In the green, it is the green graph that is, the green graph. I'm not colorblind. The pink graph that is f at x. All right. Negative 3 log base 2. So 1, we get a vertical stretch. And I'm just going to say by 3, just to say by a factor of 3 if you're watching and want to write that down. I just want to manage my space here. And then the negative 3 indicates that this is going to be reflected in the x-axis. So we can apply those one at a time. So I'll reflect first. So 1, 0 stays where it is. 2, 1 goes to -2, or goes to 2, -1. 4, 2, 4, -2. So our reflected graph looks something like that. And then we're stretching this by a factor of 3. 1, 0 doesn't move. 2, -1 goes to 2, -3. 4, -2 will go to 4, -6. Like so. This is the graph of f of x in this case. So hopefully you had something similar. If you didn't have as much detail, that's okay. But if you had the general idea, that's what's important. All right, lastly, what do we have here? Log base 2 of x plus 2 plus 2. So we have a couple translations going on. Left 2 and up 2. So if we're moving things left 2, remember the vertical asymptote gets moved as well to x equals -2. Let's pick up and move our points. So 1, 0, left 2, up 2 goes to -1, 2. 2, 1, left 2, up 2 goes to 0, 3. 4, 2, left 2, up 2 goes to the point 2, 4. All right, good stuff. So these actually we did, these graphs are actually fairly detailed. They have the asymptote, and each of these graphs has 3 anchor points that have been translated. So actually, I did show a lot of detail in these guys here. But if you just got the general idea of the transformations, that's fantastic. We're going to do some more detailed sketches of some functions and look at some properties as well. So when I give you guys an assignment or an evaluation, I'll generally give you guys, for this unit, I'll give you guys some kind of structure like this for you to follow. So the first thing we're going to do is we're going to pick off all our parameters, and so that we can do the transformations. So looking at this function here, we can see that we are not multiplying the x by anything. So k equals 1. And so our stretch or compression vector horizontally is just going to be 1 as well. We're also not stretching it vertically. A is 1. This one, we're subtracting 2. So d is 2, and we're subtracting 5. C equals -5. Now, with these kind of problems, I like to have you guys give me some anchor points. And in this case, we know, well, we've already used 3 for this base function. And maybe I'll just write that here. Our base function that we're using to sketch this is y equals log base 2 of x. We have to know some key points on this. And we know that when from our previous work, when x equals 1, y equals 0. When x equals 2, y equals 1. When x equals 4, y equals 2. Maybe can you pause the video and think of a final, just to fill up this table, what would be another point on this function? What would kind of the next point be? It doesn't fit on our page, but when we transform it, maybe it will. And yeah, I'll unpause when you're ready. If you said 8, 3, good for you. So maybe I'll just show some work up here. When you do log base 2 of 8, that's asking 2 to what exponent gives you 8, and you get 3. So when x is equal to 8, y is equal to 3. And if you'd like, you can plot those key points, 1, 0, 2, 1, and 4, 2. And if you'd like, you can add a rough sketch of the logarithmic function. 8, 3, somewhere off our page. Okay, so that's kind of like our starting point. Now, different teachers do different things. I like to apply my stretches and reflections. So we can do that all at once using the mapping rules from earlier. Now, it turns out for this one, K is 1 and A is 1. We're actually not stretching or compressing any of these guys. So with no stretch or compression to apply, our anchor points are still our anchor points. When we translate them, we're shifting them right 2 and down 5. And so we can just add 2 and subtract 5 from each of the points in the second column. So we get the point 3, -5. 4, -4, 6, -3, and I don't think this one will be on our graph. 10 and -4, -2, excuse me. Let's plot those final points on there. So 3, -5, 4, -4, and 6, -3. So it's like our graph has been picked up and moved, right 2 and down 5. Now, before we kind of make our final little sketch, remember, this is important. The asymptotes translate too. So the vertical asymptote gets translated as well. Please add that layer of detail to your graphs. And then from here, it's just connect the dots as best you can. Something like so. All right, so this is the work I expect you guys to kind of show when you're doing a graph for me on an assignment. We're also going to, that was a nice sketch. Now we're also going to take a deeper dive here, and we're going to look at some other properties of this function. So now that we've sketched it, we can talk about the domain and range. So let's do that first. So for the domain, why did I say 4? We're doing step 1. For the domain, we can see our vertical asymptote move to x equals 2, and the logarithm is only defined for, remember, the logarithm is only defined for positive values. You can't do the log of 0 or the log of a negative. So x minus 2 has to be bigger than 0, so x has to be bigger than 2. And we can see that easily now from the graph. X is a real number. X is just strictly greater than 2. For the range of the basic log function is y is any real number. Translating it up or down did not change that. The range is y is any real number. Don't know why I put 2 there. Domain and range. Let's investigate if there's an x-intercept. So the x-intercepts, do step 2 here. X-intercepts occur when y equals equal to 0. So we're going to set y is equal to 0. And what does that look like for our equation? So 0 equals log base 2 of x minus 2 minus 5. And we're going to solve this equation. So we get 5 equals log base 2 of x minus 2. And so we have to ask ourselves, so remember this is saying 2, the base is 2, 5 is the exponent, and that gives you x minus 2. So we can rewrite this as x minus 2 equals 2 to the power of 5. So x minus 2 is equal to 32. And we can actually solve for the x-intercept, 34. Now it's off our graph, but it's nice to know that detail. How am I doing for space here? Doing just fine. For the y-intercept, we'll set x equals to 0 and see what we get for y. Y equals log base 2 of 0 minus 2 minus 5. So log base 2 negative 2 minus 5. Now think if we were trying to evaluate this. Remember what log base 2 of minus 2 is asking for. It's saying 2 to what exponent gives you negative 2. No such number exists. So what we have shown here is that there is no y-intercept. Of course, we already knew that because we made the graph and the asymptote got moved to x equals 2. And speaking of that, we have shown that on our graph, the asymptote gets shifted to x equals to 2. So for the remainder of this lesson, we're going to make a few graphs, and then we're going to analyze a few properties. Moving on, maybe if it's clear that there's no y-intercept, we might not do it. But if there does appear to be a y-intercept, then maybe we'll go about finding it. We just might, we have this example, and you guys have how to find y-intercept, x-intercept. So if I maybe as we do the next few, maybe we'll gloss over one or two of those things if they're glaringly obvious that they don't exist. Now that was the previous example. We were transforming the logarithm function with the base of 2. In this question, we're going to transform the common logarithm function, the log function. So remember, guys, that the here our base function. When you just see log, there's an implication that it's log base 10. Log base 10 of x. We just don't write the 10. It's a common logarithm. When you see log x, we know it's log base 10. Now, log base 2 of x had some anchor points with pretty low numbers that we can use. In our question here, we're going to make use of 2 anchor points. All basic log functions go through the point 1, 0. And that's because anything to the power of 0 is equal to 1, right? If you think about what log base 10 of 1 is, 10 to what power gives you 1? 0. And we also will get a second point. The next kind of best thing we can do is log base 10. We know that 10 to the power of 1 is equal to 10. And so we get 2 anchor points, 1, 0 and 10, 1. And those will be the only guys we have on here, 1, 0 and 10, 1. Now I might regret this, but I'm just gonna try to add on this basic function here. I think I can do a little better. A little trickier to sketch these when they're so flat. That actually isn't half bad. All right, so for the next few examples, we're going to be our base function will be log x, and we're just going to use these 2 anchor points combined with the vertical asymptote. It's going to be enough detail. So what do we got here? We are multiplying the log by 5, so our a value is 5. Nothing is multiplying the x, so k is 1. So we got no horizontal stretch, compression, or reflection. We are subtracting 3 off the x, right? Or subtracting -3. X subtract -3. That's like x plus 3, right? Maybe I'll even rewrite that up here. X minus 3. And then finally c. There's no value on the outside, so we're not translating at all. So what we have here is it looks like we're applying a vertical stretch, and then we're translating left 3. Now just graphing that as you see it is like we could just do that, follow those instructions on our graph right now. I like having this kind of structure with this table to see how things transform. So let's do the next one. So we are only stretching the y values out. So 1, 0 will stay at 1, 0. But 10, 1 is going to go to 10, 5, multiplying the y value by 5. So that will stay here. 10, 1 will go to 10, 5. And so I'll just add in that iteration. Stretches it up a little bit, makes it a bit easier to draw. Okay. And then we're translating left 3. So we'll be subtracting 1 from the exponents. I'll just use red maybe for this one. Subtracting 1 from the x value, excuse me. So 1, 0 will go to -2, 0. We're only doing a shift left. 10, 5 will go to 7, 5. And I'll maybe put this work down here. The vertical asymptote will go from, it was at x equals 0, but if we're shifting it left 3 units, is now going to go to x equals -3. So let's draw that detail in, not just the anchor points, draw in where the asymptote is. -2, 0, and 7, 5. So we applied the stretches, reflections first, and then we translated. And I have mine color-coded here. You may wish to label your 3 iterations on your piece of paper. Ultimately, if you just plot the final graph, that's totally okay with me. In fact, maybe for the next one, we'll do what I consider to be like minimal work. But what are the key features of this function? So domain and range, pretty straightforward from the graph. X is bigger than -3. Y is any real number. The asymptote we've already talked about. But can we scratch out what and obviously the x-intercept is pretty clear. It's at -2, 0. All those things pretty obvious. So vertical asymptote, x equals -3. The x-intercept, we can just read off -2, 0. Again, those things are pretty easy to see. What about the y-intercept? Not as obvious. Well, let's find it. Let's see if we can find it. So for the y-intercept, and again, we know it exists. We can see from the graph. So let's set x equal to 0. And so y equals 5 times the log of 0 plus 3, which is equal to 5 log 3. Now, log 3 is saying 10 to what power gives you 3? Obviously, we don't really know that off the top of our heads, but your calculators do have a log button, and we can just get that approximately so we can just check our graph. If you do 5 log 3, so 5 log 3, I got about 2.3, about 2.4, 2.39. So 0, 2.39. It definitely seems to fit with our graph. All right. So let's continue, guys. We're just going to do a couple more, I believe. Pick off some properties, just get some more practice. I didn't change this one. For B, I'll change it on your lesson sheet. What did I have it changed to? So this will be updated on your lesson sheet. I just got to fix it on mine. Y equals log of -2x plus 4. Okay. Yeah, that'll be fixed on the lesson sheet I post. All right. So we are transforming the common log function, y equals log x. The anchor points will use the same two, 1, 0, and 10, 1. What are our parameters? So in this one, we are multiplying the x by something. K is -2, which makes 1 over k -1 over 2. So we know a couple things. We're going to have a reflection in the y-axis, and our function is going to be compressed horizontally, and nothing in front of the log. A is 1. No horizontal translation, but there's a vertical translation of 4 units. Now, I said for this one, I'd show minimal work. So let's just see where those points transform to. And then, you know what, what I'm going to do is I'm going to graph what I can. So 1, 0, here's the original. And then I'll kind of erase them after the fact and just show you what is acceptable to me just for you guys to do. So there's not much we can show there. When we do the reflection and stretching, so we're multiplying the x by 1 over k. So 1, 0 will go to -1 over 2, 0. And 10, 1 will go to -5, 1. So -1/2, 0, and -5, 1. And not used to drawing them this way. That wasn't half bad. So that's what that transform function looks like for that first stage, applying all the stretches, compressions, reflections. And now we just have to translate, and we're only shifting these up 4 units. So -1/2, 0 will go to -1/2, 4. -5, 1 will go to -5, 5. Up here, and -1/2, 4. And that's it. And it shoots down towards the asymptote. Something like that. And that's our finished product. And we can, as far as the vertical asymptote goes, because the graph was not shifted horizontally, the vertical asymptote is still x equals 0. Now, what I would consider to be kind of minimal work is I don't really need you guys to show me the intermediate steps. You can use the table to keep track of, what happens after I reflect and stretch. We got those 2 points there. What happens after I apply the translations? We have the points there. If you guys just plot the finished product, I'm okay with that as long as you show this work in the table. And I just made a statement of where the asymptote is. What are the key features? Okay, so a couple things. One, we already know the vertical asymptote. Two, it is clear from the graph, because of our vertical asymptote being at x equals 0, that there is no y-intercept. Hopefully that's clear. There is an x-intercept. It's not obvious where it is, so let's find it. Domain and range are kind of clear as well. X is less than 0, y is any real number. But let's set y to 0 and see what we get. So 0 equals the log of minus 2x plus 4. And so rearranging this, I get negative 4 equals the log of negative 2x. All right, and now let's rewrite this in exponential form, because right now clearly not obvious what satisfies this. So remember, for your common logarithm, log the base is 10. 10, the exponent negative 4 equals negative 2 times x. And so we're basically almost done. 10 to the power of negative 4 is 1 over 10,000. And solving for that, we get x equals negative 1 over 20,000. So that's a little hard to show on a sketch there, but we did, we did our best. As I mentioned before, some of these details like x-intercept, y-intercept, not easy to read off a graph. You can estimate them, but not very reasonable for us to plot. And here we can see it's already bumping very close up to the asymptote. Okay, one more. Let's look at this last log function. And maybe for this one, I would encourage you guys, once we have it set up, to try it on your own. But I've been intentional here, including one of these questions. We have to make sure that when we're sketching, and this is true for any function, but for log functions, we want to make sure we're in the form log k times x minus d plus c. We need to have the inside factored so that we can read off the appropriate horizontal translation. So here, we need to rewrite the inside of that log as 2 times x minus 2. So in this case, we get a k value of 2. 1 over k is 1 over 2. And everybody would have been okay there. A value is 1. But here we can see by factoring that the d is actually 2. We have a translation right to. A common mistake here is to see, my shift must be 4 units, right? No, we have to have it in that form. And c is 0. So yeah, if you guys want to pause the video, can you take our anchor points and our our vertical asymptote that's normally at x equals 0? Can you guys find those transform points? Can you guys find the new vertical asymptote? And if there is an x-intercept and a y-intercept, can you find them? So yeah, pause the video and please give it a try. But I'm going to go through that right now. So spoiler alert, here we go. I kind of do enjoy just having a visual of what the function looks like. 10.1 is just going to be somewhere over here. I'm just going to add it in. That wasn't half bad, actually. Okay, there's my base function. Let's apply these stretches and reflections. All we're doing here is compressing the x values. So 1, 0 will go to 1 half 0. 10, 1 will go to 5, 1. So 1 half 0 and 5, 1. So we get a bit of a compression. Good enough. And then finally, we're translating things right to units. That will get us to 2.5, 2.5, or 5 halves. Still 0. And will get us to 7, 1. So this actually might be even a good candidate for, things are getting a little clunky here for sure. 2.5 and then 7 and 1. The vertical asymptote has gotten moved to, we're shifting things right to, so it goes to x equals 2. Dash there. And we'll connect the dots right there through that like so. All right. Key features. So hopefully it's clear to you guys. Much like our first example, there's no y-intercept. The asymptote's at x equals 2. The graph is beyond x equals 2. So there's no y-intercept. I don't think we need to show any work mathematically proving that. No y-intercept. Vertical asymptote we have. Domain and range, pretty easy to visualize. X is greater than 2. Y is any real number. And you know what? Might be a good talking point just quickly. It might look like this graph is flattening out and that it's going to eventually stop increasing. It does flatten out, but the log function does increase forever. If you name a y value, there is an x value that eventually will produce it. It just takes a long time. So they're the y values do span all the numbers. Let's find the x-intercept, and I think we'll call it a lesson. Set y equal to 0. 0 equals the log of, we can use the original, 2x minus 4. So what does this mean? Base of our common logarithm is 10. 0 is the exponent. This gives us 2x minus 4. So in our last lesson, I asked you guys to try to practice a lot of that, converting back and forth between log form, exponential form. It's useful here. 10 to the power of 0 is 1. 1 equals 2x minus 4. Move the 4 over. And what I just realized as I'm mathematically doing this is that one of our anchor points actually got transformed to this one. So we actually already knew the y-intercept, but maybe it was a good exercise just to verify that. Just good practice maybe on the whole. All right, guys. So my expectations of you guys, given a transform logarithm function, obviously I expect you to make a detailed sketch. If I ask you guys to do this and where I'm going to evaluate it, I'm going to provide you guys a structure like this. And I want you guys to use a similar method we did in class. And I might also ask you for domain and range, the new equation of the asymptote. And if there is an x-intercept and a y-intercept, I will ask you guys to solve for it using the techniques we've learned in class. All right. Just summarizing what we did, just a review of the different transformations as they apply to the logarithmic function. And it's the same as they always are. And for graphing, in my opinion, I agree, it's easier before multiple transformations in a series of steps. I like to do the stretches, compressions, reflections kind of all at once. We can take care of that by multiplying the x values by 1 over k and the y values by a. Then we can apply the transformations in step 4. So I like doing steps 1 to 3 all at once. And again, that maps those points right to just using that transformation. It takes care of all the stretches, all the reflections, and then all you have to do is translate. So I have some suggested practice for you guys to try. I'll also have a assignment for you guys on graphing some transform logarithmic functions. Okay, that's it for this lesson. Hope you enjoyed. I enjoyed giving it. Please reach out if you need a hand. Take care, guys, and we'll see you soon.